The paper of the day is Brewer's Conjecture and the Feasibility of Consistent, Available, Partition-Tolerant Web Services. When designing distributed web services, there are three main properties that are commonly desired: consistency, availability, and partition tolerance. It is impossible to achieve all three. In this paper, they prove this conjecture in the asynchronous network model and then discuss solutions to this dilemma in the partially synchronous model. At PODC 2000, Brewer, in an invited talk, made the following conjecture that it is impossible for a web service to provide the following three guarantees: consistency, availability, and partition tolerance. All three of these properties are desirable and expected from the real-world web services. Most web services today attempt to provide strongly consistent data. There has been significant research designing ACID2 databases, and most of the new frameworks for building distributed web services depend on these databases. Interactions with web services are expected to behave in a transactional manner. Operations commit or fail in their entirety, that is, they're atomic, and transactions never observe or result in inconsistent data. Uncommitted transactions are isolated from each other, and once a transaction is committed, it is permanent, that is, it's durable. It is clearly important, for example, that billing information and commercial transaction records be handled with this type of strong consistency. Web services are similarly expected to be highly available. Every request should succeed and receive a response. When a service goes down, it may well create significant real-world problems. The classic example of this is the potential legal difficulties should the e-trade website go down. This problem is exacerbated by the fact that a website is most likely to be unavailable when it is most needed. The goal of most web services today is to be as available as the network on which they run. If any service on the network is available, then the web service should be available. Network partition. Finally, on a highly distributed network, it is desirable to provide some amount of fault tolerance. When some nodes crash or some communication links fail, it is important that the service still perform as expected. One desirable fault tolerance property is the ability to survive a network partition into multiple components. In this paper, they will not consider stopping failures, though in some cases, a stopping failure can be modeled as a node existing in its own unique component of a partition. So here's the theorem 1. It is impossible in the asynchronous network model to implement a read-write object that guarantees the following properties: that it's available and atomic consistency in all fair execution, including those in which messages are lost. The corollary for this is it is impossible in the asynchronous network model to implement a read-write data object that guarantees the following properties: availability in all fair executions and atomic consistency in fair executions in which no messages are lost. The solutions in the async model: when it is impossible to provide all three properties, that is atomicity, availability, and partition tolerance, any two of these three properties can be achieved, that is atomic and partition tolerant. If availability is not required, then it is easy to achieve atomic data and partition tolerance. The trivial system that ignores all requests meet these requirements. However, we can provide a stronger liveness criteria, that is, if all messages in an execution are delivered, the system is available and all operations terminate. A simple centralized algorithm meets these requirements. A single designated node maintains the value of an object. A node receiving a request forwards the request to the designated node, which sends a response. When an acknowledgement is received, the node sends a response to the client. Many distributed databases provide this type of guarantee, especially algorithms based on distributed logging or quorums. If certain failure patterns occur, then the liveness condition is weakened and the system no longer returns responses. If there are no failures, then liveness is guaranteed. Solutions in async model: atomic and available. If there are no partitions, it is clearly possible to provide atomic and available data. In fact, the centralized algorithm meets these requirements. Systems that run on intranets and LANs are an example of these type of algorithms. Available and partition tolerant. It is possible to provide highly available and partition tolerance. If atomic consistency is not required, if there are no consistency requirements, the service can trivially return V0, the initial value in response to every request. However, it is possible to provide weakened consistency in an available partition tolerant setting. Web caches are one example of a weakly consistent network. The impossibility result. It is impossible in the partially synchronous network model to implement a read-write data object that guarantees the following properties: that it is available and it is atomically consistent in all executions, even in those in which messages are lost. Looking at the contribution, this paper shows that it is impossible to reliably provide atomic consistent data when there are partitions in the network. It is feasible, however, to achieve any of the two of the three properties, that is consistency, availability, and partition tolerance. In an asynchronous model, there are no clocks available. In the asynchronous model, when no clocks are available, the impossibility result is fairly strong. It is impossible to provide consistent data, even allowing stale data to be returned when messages are lost. However, in partially synchronous models, it is possible to achieve a practical compromise between consistency and availability. In particular, most real-world systems today are forced to settle with returning most of the data most of the time. Formalizing this idea and studying algorithms for achieving it is an interesting subject for the future theoretical research.